What specific problem does the proposed method aim to solve?
The proposed method aims to solve the problem of generating images and videos with consistent characters in terms of both identity and attire, while maximizing the controllability of the user via text prompts. The method targets maintaining subject consistency in multiple images to effectively narrate a story, which is a challenge faced by existing models in text-to-image and video generation tasks. The goal is to create a lightweight solution with minimum data and computational cost, or even in a zero-shot manner, to address the issue of generating subject-consistent images and videos for storytelling. The method introduces consistent self-attention, which builds correlations across images within a batch to generate consistent character images in terms of identity and attire, enabling the generation of subject-consistent images for storytelling. Additionally, the method proposes a semantic motion predictor for video generation to predict transitions between two images in the semantic space, aiming to generate smooth video frames with significant improvements over existing conditional video generation methods.
How does the proposed consistent self-attention work, and how does it enhance the generation of subject-consistent images?
The proposed consistent self-attention works by sampling tokens from other images within a batch and incorporating them into the keys and values during self-attention computation. This allows for building interactions among images within a batch to maintain subject consistency. By pairing the sampled tokens with the image features, a new set of tokens is formed, which undergo linear projections to generate new keys and values for consistent self-attention. This process enables the model to perform self-attention across a batch of images, facilitating interactions among features of different images. As a result, the model converges characters, faces, and attires during the generation process, promoting the generation of subject-consistent images. The consistent self-attention enhances the generation of subject-consistent images by efficiently preserving the consistency of characters in terms of identity and attire across multiple images, which is crucial for storytelling.
What are the theoretical or practical benefits of using consistent self-attention compared to existing methods in image and video generation?
The theoretical and practical benefits of using consistent self-attention compared to existing methods in image and video generation are significant. The consistent self-attention module allows for the generation of subject-consistent images with consistent characters in terms of identity and attire, while maximizing user controllability via text prompts. This is achieved in a training, free and pluggable manner, which reduces the computational cost and data requirements compared to methods that rely on extensive training or fine-tuning. By building correlations across images within a batch, consistent self-attention promotes the convergence of characters, faces, and attires during the generation process, leading to highly consistent images that effectively narrate a story. Additionally, the consistent self-attention module facilitates interactions among features of different images, enhancing the overall consistency and quality of the generated content. In video generation, consistent self-attention contributes to the creation of smooth transition videos by maintaining spatial information and accurately predicting intermediate frames based on the image semantic space. This results in videos with better continuity and physical plausibility compared to methods that solely rely on temporal modules for predictions. Overall, consistent self-attention offers a lightweight and efficient solution for generating subject-consistent images and transition videos with improved controllability and quality, making it a valuable addition to the field of image and video generation.
How is the semantic motion predictor utilized in video generation in the proposed framework?
The semantic motion predictor in video generation within the proposed framework is utilized to encode images into the image semantic space to capture spatial information for accurate motion prediction. The RGB images are first encoded into vectors in the image semantic space using a function E, which maps the images to the semantic space. A pre-trained clip image encoder is utilized as E to enhance performance through zero-shot capabilities. The start and end frames are compressed into image semantic space vectors K_S and K_E. A transformer-based structure predictor in the image semantic space is then trained to predict each intermediate frame by linearly interpolating the start and end frames into a sequence and passing it through transformer blocks. The predicted frames in the image semantic space are then decoded into the final transition video using a video diffusion model, where image semantic embeddings are positioned as control signals and involved in cross-attention of UNet. This process enables the model to better model motion information and generate smooth transition videos with large motion by leveraging spatial positional relationships encoded in the image semantic space.
What were the results of the quantitative and qualitative comparisons of the proposed method with existing methods in image and video generation?
The results of the quantitative and qualitative comparisons of the proposed method with existing methods in image and video generation were highly favorable for the proposed method, StoryDiffusion. In terms of image generation, the qualitative comparisons showed that StoryDiffusion consistently generated highly consistent images with subject-consistent characters, maintaining both identity and attire, while other methods like IP, Adapter, and PhotoMaker struggled with inconsistencies in attire or diminished text controllability. Quantitatively, StoryDiffusion outperformed the existing methods in both text, image similarity, and character similarity metrics, showcasing its robustness in maintaining character consistency and adhering to prompt descriptions. Regarding video generation, the qualitative comparisons demonstrated that StoryDiffusion significantly outperformed sane and sparse CTRL by generating smooth and physically plausible transition videos with excellent continuity and consistency. Sane and sparse CTRL exhibited issues like corrupted frames or inconsistencies in appearance, while StoryDiffusion succeeded in generating videos with very smooth motion and maintaining spatial relationships. In quantitative comparisons, StoryDiffusion outperformed the other methods across various metrics, including LPIPS and CLIPSIM, indicating its strong performance in generating consistent and seamless transition videos. Overall, the proposed StoryDiffusion method showed superior results in both image and video generation compared to existing methods, as evidenced by both qualitative and quantitative evaluations.
What are the limitations or drawbacks of using consistent self, attention, and semantic motion predictor in the proposed StoryDiffusion framework?
The limitations or drawbacks of using consistent self-attention in the proposed StoryDiffusion framework include the potential impact on the diffusion process due to the sampling rate. A lower sampling rate, such as 0.3, may not effectively maintain subject consistency in generated images, as observed in the ablation study. This suggests that the sampling rate needs to be carefully chosen to balance consistency and computational efficiency. Additionally, while consistent self-attention is training, free, and pluggable, it may still introduce some level of complexity in the diffusion process by incorporating sampled tokens from other images within a batch during self-attention computation. This could potentially increase computational overhead and memory usage, especially when scaling up to handle larger datasets or more complex scenarios. As for the semantic motion predictor in the StoryDiffusion framework, one limitation could be the reliance on encoding images into the image semantic space using a pre-trained clip image encoder. While leveraging the zero-shot capabilities of clip can enhance performance, it also introduces a dependency on the quality and generalization ability of the pre-trained encoder. If the encoder fails to capture all relevant spatial information or semantic relationships accurately, it may lead to suboptimal motion predictions and impact the overall quality of the generated transition videos. Additionally, the transformer-based structure predictor used in the semantic motion predictor may require fine-tuning or optimization to handle diverse and complex motion patterns effectively, which could add complexity to the training process and potentially limit the model's performance in certain scenarios. In summary, the limitations of consistent self-attention in story diffusion include the impact of the sampling rate on subject consistency and computational efficiency, while the semantic motion predictor may face challenges related to the quality of the pre-trained encoder and the complexity of handling diverse motion patterns effectively.